Okay, so this is the tutorial to find the internal loadings at a certain point in the body. So here you are given a pipe with the known geometry, and we apply the external load at point A here. And on the other end, at point C, we apply the fixed support. Then it is required to check the internal loading here at point B. So what we have to do, in our meeting, we use the force transmissibility principle and moment couple to solve the problem. But it seems that those concepts seems to be difficult to apply, right? So here I will give another point of view to find to solve the problem here. Okay. So the first concept is that if this body in statically equilibrium condition, then each point in this body also in statically equilibrium. That means if we slice the body and observe the section at B, there must appear force and moment that will cancel out all this external moment. Okay, so there will be reaction force and moment at point B, which cancel out, which make a zero condition of force and moment. Okay, so that's the first principle, statically equilibrium condition. Applied at every point. Okay, so now let's take a few. Let's observe this part of slicing. Okay, so let's take a look on this sliced part from point B to point A. Okay. Then next, let's evaluate using statically equilibrium. So for sigma L in X direction, so first we have to put the reference for determining the direction of force and moment here. So here we have, for example, here is the X direction and here is Y direction and here is the Z direction. Okay. So the X, Y, and Z direction. Okay, so now let's continue to have the evaluation of the statically equilibrium condition. So sigma F, the total force that work in X direction on this body must be equal to 0 to maintain the statically equilibrium condition. Then, if we assume that the positive direction is along this x-axis, along this direction of x-axis, then here we check whether if we found the external force applied in x direction. But we don't find it, right? There is no force in x direction. So the reaction force here in x direction also 0. So there is no reaction force in x direction at point B. Okay. Equal to 0. Sorry. Okay. So there is no reaction force at point B in x direction equal to 0. Then how about in y direction? Sigma f in y direction. The total must be 0 in order to be in statically equilibrium. Okay? And here we obtain that the external force applied at point A is 30 Newton in y direction. So at point B, there must be a reaction force appear here in opposite direction. Okay, with the same magnitude of 30 Newton. So we have here F at point B in y direction is equal to 30 Newton. But this is minus because it is opposite with the external load. Okay. Then next, sigma F in z direction also equal to 0. The sum of forces in z direction must be equal to 0 in order to maintain statically equilibrium condition. And we observe here that we have the external force of 50 Newton acting in the minus z direction. So there must appear, there must be, we will have the reaction force here to balance this force in the opposite direction. So here we will have the 50 Newtons. We will have the 50 Newtons of force. Where did it come from? So we will use this one. F at point B in z direction is equal to 50 Newton. So to balance out this force. Okay, so now for force analysis already in equilibrium. Okay, but we know that this force at point A must create another effect, that is the moment effect, the turning effect. So we have to evaluate the moment which is generated by this external force. Okay, so let's now evaluate sigma n on each direction. Okay, now let's take a look. Sigma moment in x direction must be equal to 0. Okay, and counterclockwise will be the positive moment. So here we have positive 17 Newton meter of moment applied at point A. So here we have 70 Newton meter applied at point A. Then what another moment which works in the direction of X. So let's see, how about this force? It creates moments or not? Yes, it creates turning moment, but the direction will be in z direction. It rotates in this direction, okay, in z direction. So we can skip this effect of this 30 Newton. How about this 50 Newton of force? It will rotate this pipe in y direction. So we can also neglect this effect in x direction. So then we need another moment applied at point P. We call this the reaction moment at point P in x direction to balance or cancel out this external moment. So here we have the mp in x direction equals to minus 70 Newton meter. Okay. So because it is work in the minus direction, so we have to draw it here. Or to differentiate the line for force and the moment, I use another color to represent the moment here. So this is the moment to balance the external moment of 70 Newton meter. So it will rotate in this direction, and here is mdx minus 70 Newton meter. And now, how about sigma moment in y-axis? Okay, in previous investigation, we know that this force create moment with respect to y-axis. So we will use this in the analysis. So this 50 Newton of force create rotation along this y-axis in a counterclockwise direction. So it will be in the positive y-axis. So that we have positive external moment due to this force with this distance. And this moment must be balanced at point B. So here we have m at point B in the direction of y equal to 0. So here we have to put, we have to put the moment at point B in y direction as minus of 62.5 Newton meter, because it is in the negative direction, so we have to put the moment here. So we have to put it here. And the direction of rotation should be like this one. So this is the moment at point B in y direction. And next is sigma moment in z direction must be equal to 0. So then we have to find the external load which create moment in regard with respective of z-axis. Okay, and this is the 30 Newton of force that create moment on z-axis, and the moment is in the counterclockwise direction. It is positive, so we put here 30 Newton times the distance from point B. It is 1 and 25, and it must be balanced by the moment at point B in z direction. So moment, the reaction moment at point P in z direction will be minus 37.5 Newton meter. Because it is negative, so we have to draw the moment, the reaction moment here. Okay. So it will rotate in this direction. So this is moment created a direction moment at point P in Z direction. So now everything already done, we can obtain the internal loading at point B. Okay, so to summarize the result, the internal loadings at point B will be this force 30 Newton and 50 Newton in Y and Z direction to oppose the external load here. And also we have 3 different moments in X, Y, and Z direction to balance out the moment given by the external loading. Okay, so I think this method is much simpler than transmitting each force into the point of application at P. Okay, so please use this to solve the problem instead what we use in the discussion in the class. Okay, see you in the next tutorial.